All right, here we go. Long-awaited Module 9 lecture. Um, so Module 9 is all about cyclohexane rings. So turns out cyclohexane rings are relatively quite stable compared to smaller rings and even larger rings. Cyclohexane rings are probably the most common rings that you'll see in organic molecules. Um, and so if you're watching this, the first thing you're going to want to do is build a model and do this with a model in your hand, um, rather than just try and follow along without having a model. So to build a model, you're going to take 6 carbon atoms, put them together in a ring, and you want to put hydrogens in all the other empty spots. So it's going to be C6H12. Your model should look something like this. If you look at it from above, you might see a hexagon with some atoms pointed directly towards you and some pointed directly away from you. If you look at it from the side, you might see this. So once you build that model, and if you're watching this in class, then I can come over and actually help you put it into a chair conformation. If you're watching somewhere else, then you can try and put it in this conformation shown on the board. But there should be 3 atoms that have 3 carbon atoms that have hydrogens pointed straight up. So that would be these 3 here, straight up, and then on the alternating carbon atoms, there should be hydrogen atoms pointed straight down. And if you get it to look like that, that's the way cyclohexane likes to hang out. And what we do is we call this the chair conformation. I'll point out in a minute why we call it the chair conformation. But this is the most stable conformation of cyclohexane. And the reason it's the most stable conformation is if you look down any single one of the carbon-carbon bonds in that ring, you'll notice that they are all staggered. So pick any 2 carbons, look down the bond, and you'll see that bond is staggered. You can't do this with any other ring other than a 6-membered ring. In any other ring, you're going to have some bonds that are eclipsed or at least partially eclipsed. But a chair conformation is especially stable because it's got because every bond is staggered. All right. So this we call the chair conformation. And it's especially stable because every bond is staggered. So where does this name chair come from? Well, we tend to draw them like this yellow drawing down on the bottom left here. And you might say, well, why do we tend to draw it like that? So here I'm going to show you by the magic of PowerPoint how these 2 correspond. So the drawing in yellow matches up with this perspective of the molecule. All right, and in this perspective, what this means is that the 2 carbons over here, I'll mark them in red, this one and this one, those 2 carbons are further away from the viewer. Oops. And the 2 carbons here, those are closer to the viewer. that's our convention. Why do we call it the chair? Well, if you draw it in the right way, it sort of looks like one of those folding beach chairs. You could draw it like this, and you could imagine a little person sitting in this chair, laid back, arms behind his or her head, just lounging on the beach. That's why we call it the chair conformation. I didn't come up with that. Someone else decided that would be the name. But we have a convention for how we draw these things. Okay? We're used to drawing things from this first perspective. We're used to drawing six-membered rings as hexagons. And then we'd have some things coming towards us and away from us as either wedged bonds or dashed bonds. In the chair structure, we don't use wedges and dashes. We're indicating perspective by recognizing that the two bottom carbons over here are in front and the two top carbons over here, the ones in red, are in back. They're farther away from us. When we draw it, these are strict conventions for how to draw these structures. Every chair structure should be made of 4 sets of parallel lines. All right? The actual ring itself is only 3 sets of parallel lines. But then when you add in the substituents, you get the 4th set, which are the ones that go straight up and down. All right? So if you look at these two, the way I've drawn them on the board, at each carbon, and it might be a little easier to see if I turn out the lights for a minute. At each carbon, I've got a red bond, which goes straight up or straight down. I've got a green bond, which is going at an angle here. I'll highlight them as I talk about them. So I've got the green bonds here. I've got the red bonds that go straight up and down. I've got these purple bonds here. 2 of them in the ring and then a couple of them coming off the ring. And then I've got my blue ones here, 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 and here. So chair structures always consist of those 4 sets of parallel lines, and at each vertex you'll see that there is one of each color represented. So when you draw these, it's important that all the lines you draw are parallel to what they're supposed to be parallel to. And the only way to get there is through practice. So it's important that you draw these things over and over. You ask me to critique them. All right, so some terminology. We have what we call axial substituents and equatorial substituents. Axial substituents, these are the things that go straight up and down. All right. If I go back to my original drawing here, the axial substituents were the ones where I drew these arrows. If you imagine spinning this thing around an axis, if it had an axis going through the middle of it like a wheel, those would be the things that are parallel to the axis that it would spin around. And just like the Earth, the things that are around the center, we call equatorial. So axial substituents are vertical. Equatorial substituents, those are the ones that are either red or blue or purple, or sorry, blue or green or purple. So my equatorial substituents in this drawing are blue or green or purple. Those come off around the middle.